A dynamical system is a system in which a function describes the time dependence of a point in an ambient space, such as a parametric curve. Mathematical models describing the motion of a swinging clock pendulum or a flow of fluid through a pipe are expressed using differential equations, and they're typically not easy to solve. So today, I'd like to show you how linear algebra is a calculus game changer. The universe is a place seething with oscillators, objects that exhibit a repetitive pattern, objects that move back and forth about some point of equilibrium, from stereo speakers to pendulums or the metronome of a clock, or the ebb and flow of the ocean. Simple harmonic oscillators provide a blueprint for circular or wave-like motion. And to illustrate a mechanical example, we consider a mass attached to a spring. You see, a spring is a restorative force, and it is one of the best examples of simple harmonic motion. So a simple harmonic oscillator, given by a spring with a mass attached to it, has a displacement of that mass we'll call x. And therefore x prime will represent its velocity. X double prime, its acceleration. And so, for a spring, the restorative force is one that is proportional to its displacement. So F spring is equal to negative kx, where k is called the spring constant. Now perhaps if this mass were moving along a surface, then that motion would be considered damped due to some frictional forces that may be applied. And so if there are some frictional forces or dampening forces, then they'll be proportional to the velocity x prime. And we can write that force as b times x prime. Third, if we consider Newton's second law of motion, force is equal to mass times acceleration, or m times x double prime, we can then take all of these components and put them into an equation for a damped harmonic oscillator. mx double prime plus bx prime plus kx equals 0. And this is an example of a second order homogeneous differential equation with constant coefficients. Our next discussion will be on linear algebra, and it begins with a system of equations. A system of linear equations. If a system of linear equations has a unique solution, such as ax plus by equals alpha and cx plus dy equals beta, if there is a unique solution, it will be the point of intersection of these two lines, a point xy which will simultaneously make both equations true. If, however, the lines happen to be, parallel to each other, that is, if they have the same slope, then they will never cross, and so we will say that there is no solution to this system. This system is considered to be inconsistent. And finally, if the two equations describe the same line, that is, really there is only one equation of a line, then it is said that the system has an infinite number of solutions, that there exists where all the points on the line are the solution. And when this happens, we call this system consistent but dependent. And so, in a system of linear equations, these are the three types of outcomes that we can have. We will see later on that these concepts transfer over to when we solve a system of differential equations. But next we take our system and reformulate it into a matrix equation. The matrix A, known as the coefficient matrix, encodes everything we need to know about the system, and thus we can use it to determine the nature of the solutions. If the system has a unique solution, its determinant will not be equal to 0. That is, AD minus BC will not equal 0. But if the determinant equals 0, then we cannot determine if it has a solution or not. In other words, if the determinant is equal to 0, the system itself is indeterminate, which is to say that more investigation is needed. With that being said, in the special case where alpha equals beta equals 0, we always have an infinite number of solutions of the equation A times the vector with xy equals the vector with 0, 0, when the determinant of A is equal to 0. Now indeed, if the coefficient lowercase a of matrix A is non-zero, then we have x is equal to negative b over a times y. And so substituting that back into the second equation gives us AD minus BC times y is equal to 0. So since the determinant of A is equal to 0, the solutions of the equation assume the form where the x component is negative b over a times y, and the y component is arbitrary. This says that every solution lies on a straight line through the origin in the plane. That brings us to the concept of linearly independent vectors. Let v and w be vectors in the plane. V and w are linearly dependent if either v or w is the zero vector, or if v and w lie on the same straight line solution through the origin. Another way to say that is, the two vectors, if they are linearly dependent, one is a scalar multiple of the other. So here w is a positive scalar multiple of v, where here u is a negative scalar multiple of v, both living on the same straight line through the origin. Linearly dependent vectors. Two linearly independent vectors therefore do not lie on the same line through the origin. That is, they do not point in the same direction or in opposite directions. So we can express this concept mathematically by saying this: vector v is not equal to a scalar multiple of vector w, if and only if vectors v and w are linearly independent, and lambda can be any real number. If v and w are given by matrices or vectors, then the determinant of the matrix that is formed by the combination of those two will not be equal to 0. That is to say that if these two vectors are linearly independent, then the determinant with their components will not equal 0. Linearly independent vectors are said to form a basis for R2, since any vector z has a unique set of coordinates relative to the independent vectors v and w. These coordinates are a pair called alpha beta, for which any vector z can be written as a linear combination of alpha times v plus beta times w. That is, z is a linear combination of the vectors v and w. A standard basis or standard unit vector basis that you might be familiar with are E1 and E2, the vectors 1, 0 and 0, 1. So planar systems in calculus, consider the damped harmonic oscillator given by the second order differential equation from before. This equation is classified as autonomous because it does not depend on time. In other words, it is not a function of time. To turn mx double prime plus bx prime plus kx equals 0 into a system of equations, we're going to first start by letting y equal x prime. Then we'll substitute into our differential equation and get y prime is equal to negative k over mx minus b over my. So now we can formulate these two derivatives together as a system of differential equations. This system of differential equations, written as x prime equals y and y prime equals negative k over mx minus b over my, is the system of differential equations which we will formulate into a matrix equation. And if this system was subjected to an external force, f of t, then our equation would no longer be autonomous. F of t would then be time dependent, and our equation would then also be time dependent or non-autonomous. So now we have a system of differential equations of first order, where capital X prime is the vector that contains x prime and y prime. And so we can then use this to visualize a system of derivatives as a vector field with a slope or direction field associated with it. Slope fields or direction fields have the vector tail ends at the coordinate points xy and are scaled accordingly. And in such a direction field, one can get a visual big picture as to what the solution curves look like, because they are exactly the trajectories that a particle would take if placed in the field and subjected to its direction field. So if our differential system has a solution vector x given by a parametric curve, then for each t, the tangent vector at each point tells the solution curve how to move, and so it winds its way through the plane accordingly to the direction field. The solutions therefore come in the form of a family of curves, which are dependent on their initial conditions. You see, for a given initial condition, we have a certain curve in that family. Perhaps an example is in order. Consider the curve given by the vector a sine of t, a cosine of t, for a being a real number. This vector is a solution to the system x prime equals y, y prime equals negative x. And we can check that by differentiating our vector x, seeing that it gives us a cosine t, negative a sine t, which is y negative x. And this solution curve describes a circle of radius a, and the slope field it is traversed in a clockwise manner when t increases. A circle of radius 0 would be a point at the origin indicating that x of t and y of t are 0 or constant functions. So now if we look at this from a point of view of a linear system, this system is equivalent to the second order differential equation x double prime plus x equals 0. And so if we had a differential equation that was non-autonomous, subject to an external force f of t, then we can still set up a system where one of those equations will be time dependent. So this is our system of differential equations formulated into a matrix equation, a first order differential matrix equation. Recall that if we have a first order differential equation, x prime equals a times x, that there exists a solution x is equal to k times e raised to the at power. And if you differentiate that, we can show that x prime is in fact equal to a times x. Now, we're going to make the claim that there are no other solutions, and we will show this by assuming that u of t be any solution And we're going to compute the derivative of u of t times e to the negative at power. The reason behind why we're doing this will become evident in a moment. But what we see here is, in computing the derivative, we get the derivative equal to 0. Now, what are the implications of that? Well, if a derivative is equal to 0, that means the thing we took the derivative of is a constant, and here the constant is k. So that if we solve that, u of t is equal to k e to the at power, proving the assertion that there are no other solutions. The collection of all such solutions make up the general solutions, whereby the constant k is completely determined if an initial condition is specified. One can suppose that a solution satisfies an initial condition, such that x of t naught is equal to u naught. Then from that we can determine the value of k and specify a unique solution. For simplicity, it is often taken that t naught is equal to 0, thus k is equal to u naught, with no loss of generality. In the world of differential equations, this is known as the initial value problem, or IVP. A solution x of an IVP must not only solve the differential equation, but it must also take on the prescribed initial value. When k is equal to 0, the special solution of the differential equation is the constant solution x of t equals 0. And it goes by a special name. It's known as an equilibrium solution or an equilibrium point. A point that is stationary, does not change. Equilibrium solutions are some of the most important in differential equations. For the system x prime equals ax, the origin 0, 0 is an equilibrium solution, and that it is always an equilibrium point for a linear system. To locate other equilibria, or stationary solutions, we must solve the linear system ax plus by equals 0 and cx plus dy equals 0. This system has a non-zero solution for the determinant equal to 0. But that would mean that there is a straight line through the origin on which every point is an equilibrium point, so we propose the following proposition. The planar system has a unique equilibrium point at the origin if the determinant is not equal to 0, and it has a straight line of equilibrium points if the determinant is equal to 0. That is, that A is not the zero matrix. So now we will return to our linearly independent vectors from the linear algebra with the concept of eigenvalues and eigenvectors. A solution is an equilibrium point when it lies on a straight line through the origin. So if we want non-equilibrium point solutions, we need to consider solutions that do not lie along the same straight line through the origin. In our linear system, x prime equals ax, suppose v naught is a non-zero vector for which we have a times v naught is a scalar multiple of v naught. Then x of t equals e raised to the lambda t times v naught is a solution to this system. Differentiating x prime shows that x prime is equal to a times x, that is, that this is a solution to our system. The vector v naught is known as an eigenvector with its corresponding eigenvalue lambda. When a linear system has a unique solution, we can find eigenvectors and eigenvalues for its coefficient matrix. Every non-zero matrix A with a determinant not equal to 0 has associated with it a set of eigenvectors with their eigenvalues. So suppose that v naught is an eigenvector of the matrix A with its associated eigenvalue lambda. Then x of t equals e to the lambda t times v naught is a solution to the system x prime equals ax. And indeed, any scalar multiple of that particular eigenvector would also be a solution. So this sets it up for a nice little example. Let's let A equal the matrix 1, 3, 1, negative 1, and we're going to find its eigenvalues and its eigenvectors. To do so, we solve the equation determinant of A minus lambda I being the identity matrix, equals 0. That leads us to something called a characteristic equation. And for a 2 by 2 matrix, it will be a quadratic, and here the eigenvalues are the roots of that equation. The eigenvalues here are plus or minus 2. So with those eigenvalues, we will now compute their associated eigenvectors by setting up the equation A times V, the eigenvector, equals the scalar value that we found for each eigenvalue times that vector. So A times V equals lambda times V, and for each vector we compute the eigenvector. For V1 we get 3, 1, and for V2 we get 1, negative 1. A pair of linearly independent vectors. So together we get to generate two different solutions, x1 and x2, using the eigenvalues and eigenvectors of the form of the general solution we spoke of earlier. So now, solving a linear system. If we have two real roots which are distinct, not equal to each other, of the characteristic equation, we may generate a pair of solutions that satisfy our differential equation of the form x equals e to the lambda t times that eigenvector, where each solution is a straight line along the eigenvector direction, and indeed we have x of 0 is equal to the eigenvector itself, which is a non-zero point in the plane. So we see here that we can set up a way of using the linear system to solve our differential equation. So for each t, e raised to the lambda t is a scalar multiple of the eigenvector, thereby emanating as a ray from the origin. And we'll note that if that eigenvalue is greater than 0, then the ray will tend to infinity as it goes away as t increases, and tend to the origin as t goes backwards in time. So we can see that the solutions definitely have the exact opposite effect when we have the eigenvalue to be negative or less than 0. And in the case where the eigenvalue is 0, then the solution is the constant function, where the solution is just the eigenvector itself. So how do we find all the solutions of a system given this pair of special solutions? This is where the linearity property will really shine. Suppose you have real distinct eigenvalues with corresponding eigenvectors v1 and v2 which are linearly independent, then they do not lie on the same straight line. Because of this, v1 and v2 form a basis for R2. By forming a basis for R2, they allow us to form linear combinations of solutions to create a new solution. That means that for any vector z0 in R2, it can be represented as a linear combination of v1 and v2. That is, that z0 can be alpha v1 plus beta v2, where alpha and beta are just some real number coefficients. So with that in mind, if we have two particular solutions, two special solutions as we discussed earlier, then the linear combination of those will also be a solution. So consider if we have the solution z of t equals alpha x1 of t plus beta x2 of t, where the x sub i's are the straight line solutions, then we can claim that z of t is a solution of our linear system x prime equals a of x. That is, that any superposition of the two solutions is also a solution. And by differentiating z here, we find that z prime is in fact equal to a times z, so that z of t is in fact a solution, and where further investigation will show that z of 0 is z sub 0. So we get the initial condition satisfied. We have a very unique solution here. We will in fact want to show that it is a unique solution. If we claim that z of t is the only solution, in other words, the unique solution of the system that satisfies z of 0 equals z naught, then how can we show its uniqueness? Well, again, we suppose that y of t is a solution which satisfies this initial condition of y of 0 equaling z naught. Then we go through the derivation showing that in fact y of t would in fact have to be equal to z of t, making it the unique solution. Pause the video now if you'd like to go through the calculations here. So now that we've kind of proven the uniqueness of this solution, we can then begin to talk about the fact that the collection of all such solutions is the general solution for our system, our initial value problem. So thus we have proven a theorem here. If A has a pair of real eigenvalues not equal to each other, their associated eigenvectors being v1 and v2, then the general solution to the linear system x prime equals ax is the linear combination given by x of t equal to alpha e to the lambda 1t v1 plus beta e to the lambda 2t v2. Recall our damped harmonic oscillator. Here, let's consider a mass of 1, a friction coefficient constant of 3, and a spring constant of 2. Let's solve this differential equation using a system of equations, a system of differential equations. So first, what we're going to do is formulate this in terms of a matrix equation, right? And we let y equal x prime, so that our differential equation gives us this system here. X prime equals y prime equals negative 2x minus 3y. Now, in its matrix form, our coefficient matrix is 0, 1, negative 2, negative 3, and solving for the characteristic equation, which comes out to be lambda squared plus 3 lambda plus 2 equals 0, we get the eigenvalues negative 1 and negative 2, two distinct, real, unequal eigenvalues. From those eigenvalues, we are then going to generate their eigenvectors by solving the eigenvector equation a times v equals lambda v. And for the eigenvector negative 1, we get the vector 1, negative 1, and for the eigenvector negative 2, we get the eigenvector 1, negative 2. Thus, we can generate a general solution of the form x equals alpha e to the negative t, 1, negative 1, plus beta e to the negative 2t, 1, negative 2. Theorem. Let our planar system have suppose y1 and y2 are solutions, and also assume that y1 of 0 and y2 of 0 are linearly independent. Then the linear combination with scalar multiples is a unique solution, and I'm not going to prove that here. But in part 2, and I hope you'll join me on the next video, we're going to discuss phase portraits and how they relate to dynamical systems. I hope you liked this video. Please hit that like, subscribe, and notification bell for more videos, and stay tuned for the next one. Thanks for watching.